Yeah, you can do that right now. Right now. So we've got a bunch to do. All right. So the first thing that we need to do is finish our guy dragging the box across the floor problem. All right. So we've got a man pulling a 50-kilogram box at a constant speed across the floor. He applies a 200 Newton force at an angle of 30 degrees. So the first thing that we did was draw a force diagram for this, where we've got gravity, the pull to the side. We talked about the fact that there's going to be an upward component of that pull and also normal force that combine to oppose gravity. And so we wrote an equation that reflected that. Next, we were asked to calculate the size of the normal force on the box. And to do that, what we need to solve for is this force here that says Fn. So we're going to need to find normal force, which is going to be the sum of minus the force of gravity minus the upward pull on the box. So we already know gravity. That one's good. We need to figure out what this FPY is. So if I look at my triangle up here at the top, I know that I've got an upward component that's going to match basically the opposite side of the triangle here. So those two things are going to be congruent. So if I've got a triangle here where the side is 200 newtons, my angle is 30 degrees, and then this side is FPY. To solve for that, I'm going to be looking at the opposite side from the angle and 200 as my hypotenuse. So if I'm using the opposite side, I'm going to need to use the sine relationship. So sine 30 equals FPY over 200 newtons. So FPY equals 200 newtons times the sine of 30 degrees, which is going to give us I got 100 newtons. So if I come back over here to this equation, I'm going to have minus 500 and then minus 100 to solve for. Minus 500 is positive 500. Minus 100 means that my normal force is going to be 400 newtons. So that would be my answer to part B. For C, it says write an equation for all the forces and components of force in the horizontal direction. So this time we're looking from side to side. So if we take a look at our force diagram, we need to think about a few more things that might be going on here. One is that we are going to have a horizontal component. So I put force, pull in the x direction, horizontal. And since we know that these forces are balanced, there has to be something that's equal in the opposite direction. And so you guys probably got this one. That's going to be friction. That's going to be the forces that are opposing that box sliding across the floor. Those two are probably going to be congruent to each other. So there's two ways that we could write an equation for this. We could write that Fpx is equal to minus Fpy, or we could write that the sum of the two, equals 0. Whoa. That's wrong. Don't write that. This one should be friction. Boo, Thursday. That kind of feels like a Monday. But that's okay because tomorrow's Friday. So that'll be like the shortest week ever, right? It feels from a Monday to Friday. Can't lose. All right, so if we add those two horizontal forces together, we should end up with 0 newtons. So that's another way to think about it. Now, it's going to be really tricky for us to solve friction at this point. So what we're going to do is solve for the other side of that triangle in that problem. And so if we've got the same triangle that we had before, Here's our 30-degree angle. We've got a side that's 200 newtons. We also know that this side is 100 newtons. You guys know the rules for 30, 60, 90 triangles? There's a rule for that. Have you guys heard of that? Yeah? Okay. So you could do it that way if you wanted to. I'm going to solve it with trig. So I need to solve for this side, FPX. So to solve for FPX, I'm going to do the cosine of 30 degrees equal to FPX over 200 newtons. So FPX equals 200 newtons times cosine 30. So it's going to be 173 newtons. Does that seem reasonable? And this is our bigger angle, so we would expect this one to be our longer side. So if that's 173 newtons, what does the other force have to be? Has to be equal to, I have minus 173 newtons, and the reason for that is because it's got to have the opposite sign of whatever's here. So the way that this actually worked out, this side ended up being negative, this side was positive, this was negative, and this was positive. As long as we have one on each side, that's okay. You guys have any questions about number 2? If you set yours up so that this FPX was a negative value, then you should have gotten a positive value here for friction, and that's fine. Okay? Sorry, you guys at home. My camera is definitely a little bit laggy, and I'm not really sure why that is. Okay, so next, determine the weight of the tram. The cable at left exerts a 30,000 Newton force. The tram is attached to the cable, so the tension in the left cable is not necessarily equal to the tension in the right cable. Well, this kind of makes sense, because if we look at our force diagram, we've got a 30,000 Newton force to the side. And then if our other cable is at an angle, then the force that's actually going to be opposite of this 30,000 is going to be on this horizontal line here. And we're going to have a vertical axis, and this is weight, right? This is our gravity, which is our weight, which is what we're asked to solve here. I'm just going to grab another color. Okay, so when we're trying to figure this out, we're trying to figure out the weight of the tram. So what we really need to know is something about our horizontal forces here. Sorry, our vertical forces. So if we draw a box around this other vector, that's going to help us out, because if we know that upward vertical component, then we know what gravity has to be, right? So how are we going to solve for that? Do some more triangles over here. So I know that is going to be the same as this one. I know that I have an angle here. This angle is 75 degrees. If that angle is 75, then this angle over here has to be 15. It's pretty short, right? This is definitely not to scale if that's the case. And we're also going to have a vector to the side that's going to be equal to this 30,000 newtons. So that's going to be the part that we know. We're going to know the side of the triangle that's adjacent to this 15-degree angle. And then we're going to solve for this vertical side. So if we have an adjacent side and an opposite side, which trig function do we need to use? Tangent, yeah. Because we're going to use an adjacent and an opposite. So to solve for this vertical piece, I don't know, force, pull, vertical. The way I'm going to set this up is tangent of 15 degrees is equal to my opposite side, FPY, divided by my adjacent side, which is 30,000 newtons. So that's going to be equal to 30,000 times tangent of 15 degrees. So I got 8,038.47 newtons for my vertical component. And so that's going to be, because that is the vertical component, if I want to solve this for FG, I could write an equation where FG plus FPY equals 0. So FG is going to be equal to minus FPY. So it equals minus 8,038 newtons. All right, what questions do you guys have so far? How are you doing on these? Doing okay? Maddie?
I just have a question about, so like the last one we did, when I was like FPY plus FN equals like negative FG.
Yeah.
You only like add these like two top components to equal like the bottom.
Yeah.
When there's like movement.
Well, not this when it has movement. Yeah, so we can add those together. For this, it's any time that it has a constant speed. So sometimes the constant speed is 0, and sometimes it has some speed, but the speed is constant. And so either of that time works. But even if it's something like a dynamic situation where it's accelerating, you'd be able to do that. We're just not going to do a lot of that in this class.
So when it's like, when time is like the normal force equals like the opposite of gravity?
It depends. If there's something else there that's supporting that downward force, then normal force could be less than gravity. So like a way that I think about it a lot of the time is normal force is the force that exists there when there's nothing else that is holding it up. And so here, this person is pulling upwards and to the side on the box. And so since there's an upward force on the box, that's going to be sort of the first choice to compensate for gravity. And then normal force fills in the rest. And we know that normal force has to be there because it's at a constant speed. And vertically, the constant speed is 0. So that's different than the horizontal constant speed. But either way, it's a constant speed. There's no change in the velocity. And so whenever we know that there's no change in velocity, we know they have to be balanced. And normal force is what accounts for the stuff that we can't account for with another force in there. I know it's one of those ideas you kind of have to like let it simmer a little bit. But that's why we can't start with assuming that normal force is anything. Because if something else is there, we have to consider that first to figure out what normal force is. Does that help? Okay. Okay, so number 4, we have a bear problem. In the space at right, draw a force diagram for the bear climbing a hill at a constant speed. So our bear is going to be experiencing gravity downward, normal force that's perpendicular to the surface. In there. And friction. Which way is friction going for him? This one's tricky. If he was just standing on the hill, then the bear would probably be trying to slide downward, right? If he was trying to slide downward, friction would be upward. Does it make a difference if the bear is climbing the hill? is when the bear pushes down with his foot. Which way is he going to push with his foot? It's the same as when we walk. Is he pushing forwards or backwards? He's going to push backwards. So friction is still going to be opposite that. So it's still going to be forward. So we're going to have friction going this way. I just drew it extra long because it probably shouldn't be that long, but then you wouldn't be able to see it because it'd be under the bear. So I just drew it like that. So if I draw my force diagram, I've got gravity. Got an axis that's going to be parallel to my surface. Normal force is going up from the surface. Friction is the opposite direction. Like that. We've got some angles in there too. If we kind of look at where our axis extends, it says that our angle is 17 degrees there, which means up here we've got a 90 minus 17 would give us 73. 73 degree angle on this guy. It's going to be our 17 degree angle again. Okay. So the first thing it says is write an equation that describes the forces that act parallel to the ramp. So we're going to have friction parallel to the ramp, right? What other things are parallel to the ramp? Well, we've got gravity here that's not sitting on our axes, so we can break it into components. So we've got gravity that's horizontal, gravity that's vertical. So I'm going to use my the component that's opposite friction. Say if I add those together, they should equal 0. For the equations that are perpendicular, for the forces that are perpendicular to the ramp, I'm going to look at my vertical component of gravity and normal force. And each of those you could write a different way. You could also write them so that you've got friction equals the horizontal force due to, equals the negative horizontal force due to gravity, or normal force equals the negative vertical force due to gravity. Lastly, if the mass of our bear is 400 kilograms, determine the value of the normal force. So if we're going to figure out normal force, we have to figure out the vertical component of gravity. And in order to figure that out, we have to figure out what the force due to gravity is. So first step is going to be that gravity is equal to our 400 kilogram mass times minus 10 meters per second squared. So force due to gravity here is going to be minus 4,000 newtons. And then if we have that value, I'm going to resketch my triangle here. We've got our minus 4,000 newtons, a triangle here with a 17 degree angle. And I'm trying to solve for this side, FGY. Well, if this is my right angle, then my 4,000 newtons is my hypotenuse, and FGY is my adjacent side. So with an adjacent side, I'm going to use cosine. So my cosine of 17 degrees equal to FGY divided by minus 4,000. So FGY equals 4,000 times cosine of 17. So I got 3,825 newtons, which seems reasonable considering how small that angle is. And this should be negative because it is downward. And so if I know that FGY is minus 3,825 newtons, then I know that Fn has to be a positive value for that. Because if I take this equation, well, I'll take this one, and make that minus 3,825 newtons, then what I end up with is positive 3,825 newtons. You guys have any questions about the bear? You guys at home doing okay? I think is this our last one? Okay. I did this a lot when I worried about uphills a lot when I was younger because I drove a car that had stick shift. And my dad was literally one of those like trial by fire, teach you how to drive people. So he was like, "All right, we're gonna drive this way," and I didn't realize what he was doing, but he took me to hills and made me drive up hills with a stick shift. I thought I was gonna die the first couple weeks, but I didn't die. I guess it worked. I don't know. Still not sure how I feel about it. But when we've got a car that's going up a hill at a constant velocity here, we're told it weighs 750 kilograms. It's going at a constant velocity, and we're told what the constant velocity is. We're also told how much friction and drag we have involved, which is really nice. Okay, so we're going to draw a force diagram for the car. So first, our car is going to be experiencing gravity. So there's Fg. We can even say how big gravity is because our car has mass that's given to us. So I like to write as much as I can on here. So we've got 950 kilograms times minus 10 meters per second squared. So our force due to gravity there is going to be minus 9,500 newtons. We're showing the direction of constant velocity there. The friction and drag that's opposing its motion. Dang, car people. Okay, so the way the cars actually work, I'm going to have to work on the wording of this problem. Make a note to self here. So I think that what this is actually saying is that since it says friction and drag, I think that it means backwards forces, which I don't really like. Friction and drag. Because there's two frictions. Then you can go ahead and go. Do you need to take your stuff with you? You'll probably be back. We have 20 minutes before the end of the grade. So we have to have something that's making the car go forward. Just like when we're walking. If we have a wheel that's turning, I'm just going to draw a random wheel down here. A giant random wheel. Okay. So if we've got a wheel that's turning on this ramp and the wheel is turning in this direction, right? The wheel is trying to go that way on the ramp. And so there's actually going to be friction that pushes upward on the car or on that wheel. And that's ultimately going to be the force that makes the car go up the hill, right? Does that make sense? I think that what this is trying to describe, friction and drag opposing its motion, I think that this means air friction. Because drag is going to be opposing the car going up the hill. And so that's probably a backwards force. I think it's poorly worded, though. I'm going to call it drag. I'm just going to drop that it's air friction. So we're also going to have friction on the car, and the friction is going to go the opposite direction. Like that. So we've got a bunch of stuff going on. Now, since our normal force is always going to be perpendicular to the surface, the best choice for axes here is the horizontal. What am I trying to say? A line here that's parallel to the horizontal forces, and then a line that lines up with normal force. So then we've got gravity slightly backward. Do you guys think that makes sense about our force diagram? So draw our force diagram. There we go. It says, what's the weight of the car? We actually already figured that out too. If you find that you're solving things other places on your paper, you could write the answer, because I always want to see your work, right? So write the answer, and then I'm going to put C above on here, just in case Dr. O'Malley didn't notice that I did it up there, because we always want to see your work. Can we figure out the normal force on the car from all this? We absolutely can. So first we have to kind of figure out where our angles go. So if this is a 22-degree angle down here, then that tells us what this angle has to be. We have to go 90 minus 22, so that's going to be 68. So we got a 68-degree angle there. And what we're going to try to figure out is normal force. So we need to figure out this downward component. And that's going to be equal to our normal force. So it's going to be Fg, and that's our vertical component, so y. So how do I draw that? I'm just going to recopy the triangle for you guys. Kind of put. All right, Fgy, or Fg, and then this part is Fgy. This angle is 68, and the thing that I know is that this is minus 9,500 newtons. Right, this downward one. So if I want to figure this side out, that's the side opposite from 68. So opposite means I'm going to use sine. So sine of 68 is equal to Fgy divided by minus 9,500 newtons. So Fgy is going to be equal to minus 9,500 newtons times sine 68. I got minus 8,808 newtons. So to figure out normal force, I know that this has to be equal in magnitude and opposite direction. So normal force is going to be minus 8,808 newtons. So positive 8,808 newtons. Now, if we want to know the force on the car that lets it go up the hill, what we need to do is figure out this force, this upward friction force on the tires. We know a value for drag, right? We're being told that there's 1,200 newtons pulling the car backward, just a drag. We also know that there's a mass coming from, there's a force coming from this component of gravity, where gravity is trying to pull the car down the hill too, right? If you've ever tried to start a car on a hill, you've probably experienced that, right? You guys ever use like a clutch or something? You have to let the brake go, and it like drags backwards a little bit before it goes forward. Sometimes even the automatics will do it. But that's also going to be present. You're not going to have drag. You guys might know this. In aerodynamics, you're not going to have drag from an object moving until it actually starts moving. And honestly, moving at kind of a little bit of speed. So that's why, yeah, 7 meters per second. It's not a lot, but it's something. So what we're going to have to do is think about what our horizontal forces are. So we're going to need to add together all three of those. We've got friction, we've got a horizontal component from gravity, and we've got drag, and those are going to add up to be 0. Sorry. The one that we're going to need to solve for here, it says calculate the force on the car that lets it go up the hill. We're trying to solve for this one. We already know what this one is. We know that this is 1,200. Also notice that we used a positive value here. So if we're using a positive value for this direction, that means we need to use a positive value. Come on. Okay, so we used a positive value for drag. So if we used a positive value for drag, we're going to also need to use a positive value for FGX because they're both going in the same direction. So we should end up with a negative value for friction because by saying that this is a positive direction, we're saying that this is the negative direction as well. Okay, so yeah, so it's as if we're using the same triangle, only we're going to calculate for the part that's parallel to the surface. So that side is going to be the cosine. So the cosine of 68 degrees is equal to FGX divided by 9500. FGX is equal to 9500 times the cosine of 68 degrees. Should have the units newtons. All right, so I punched all that stuff in my calculator that way, and I got a negative number, but I know that it should be positive. So I'm going to write it as a positive. 3,559 newtons. I rounded up because it's 8.76. So then when I solve for friction, I'm going to say minus 3,559 newtons plus 1,200 newtons equals, when I add those two together, so I have my positive number in my calculator now. I multiplied it by -1 to get rid of that, plus 1,200. So I got 4,759 newtons. How'd you guys do on that one? Okay? Most of it? I think the trickiest part in that one is realizing that you have to add together two forces. So that's what gets tricky about those. So what I'd like to do tomorrow is have a little quiz for you guys. So it's not going to be super long because we're getting right. You guys notice this? We're at the end of this. We may do a lab next week too. I'm thinking about it. We'll see. But I want to give you guys a little bit of a quiz to see where you're at so that we can get ready to do like an actual test. Does that sound okay? All right. Do you guys at home have any questions?